All right, greetings, image optics students. As promised, I think I've set up some math that I'm going to do, and I'm going to force myself to draw some of it so you can follow along. I've written out the setup of the problem, and I will draw it out and go through all the steps of solving. So, reading off the example, a 10 centimeter tall object is 60 centimeters from a two-lens system. So that means it's 60 centimeters away from the first lens. The lenses are 40 centimeters apart, and they have focal lengths of 10 and 15 centimeters respectively. So I'm going to find the location and size of the intermediate and final images. When I talked this out going through my slides, I mentioned we can treat this as two separate problems. The first lens will create an image in the middle, and that image will act as the object for the second lens. We'll find out what image that lens makes, and then we can calculate things about the final result. Okay, so one thing that'll be helpful to remind us. I went through this in class, but if you remember. Our lens equation, if I rearrange this a little bit, it was helpful to get di by itself. So if I want di by itself, I'm going to get 1 over di by itself first. I get that by subtracting 1 over do from both sides. And then the problem is we don't have a common denominator, so the common denominator is f times do. So I can make 1 over f the same as do over f times do, and then minus f for f times over f times do, like that. And so now that we have the common denominator, I have that. And this I can flip. So in general, image distance is going to be f times do over do minus f. And that should be useful more than once. So that will help me get an image distance pretty quickly. I can use my calculator to get the things that I want. Now, I'm actually going to try something a little nuts. I'm going to get this out, and using my ruler, I'm going to try to draw all of this to scale if I can. So here's what I mean by that. I'm going to say on my drawing 1 centimeter equals 10. So I'm going to make this a 1 to 10 scale drawing. Make sure my camera isn't too messed up. Oh, some key points that are going to be important. I want to know. Right, I'm going to put the object at the end of the line here. One lens is located 60 centimeters. The second lens is 40 centimeters away from that, so I'm going to put that at the 10 here. The focal point, or the focal distance, is 10 centimeters for the first lens and 15 for the second lens. So if my second lens is going to be at 10, right, 8.5 and 11.5 are the focal locations there. And for the first lens, it's just, right, 1 centimeter each way, because I'm doing this 10 to 1. All right, so roughly speaking, I have one thin lens here and one thin lens here, like this. And those are, the two lenses are 40 centimeters apart. And my object is going to be 1 centimeter big, the very end here. Now, I could use the P and Q terms, which I talked about on my slides, and they're on the lab handout. I don't think we really need to do that to get this right. The very first thing I want to do is get a sense for where that first image is going to be. So I'm going to draw some principal rays which I hope help us out. So it's not gonna be exact, but I draw one ray parallel, that gets bent through the focal point. Another ray will go through the center of the lens, undeflected. Let me recenter that so you can see it. All right, so my first ray went parallel and then went through the focal point. This drawing is not going to be perfect, but close enough. I can already tell. I have one principal ray that goes through there, and if I have like some imaginary Mellon-Taylor at the end of these, you can see that I've got a tiny intermediate image right there. It's a little bit past the focal point. It's upside down. It's smaller, and the math will prove that to us. And then I'm not going to draw the second image diagram for a reason you'll see in a minute. But this image is going to be the object for lens 2. So that will be the next part of the problem. All right. So what I have for the first case is I have an object distance of 60. The focal length for the first lens is 10 centimeters, and I want to know where that image distance is. But I've already gone through the work of a shortcut formula to figure out where that's located. If I do 10 times, 60, and then on the bottom 60 minus 10. So that's 600 over 50, and that answer is 12 centimeters. So that is where, so that means this is a 12 centimeter distance here between the first lens and where this little image is. Now, if I drew everything to scale, that means there should be 1.2 centimeters on the drawing, and that's pretty darn close. Okay, so where that arrow is, it's between 1.2 and 1.3 centimeters. So that goes along well with my prediction that the first image distance is 12 centimeters. Now then, traditionally, what do we do with that? We can say the first magnification is negative di over do, and that is negative 12 over 60, which reduces to 1/5, negative 1/5, like that. And so that image height is equal to the original height times that magnification. The original object was 10 centimeters tall. The magnification is negative 1/5, and so negative 2 centimeters is that image height. I've already messed up my web camera. Let me recenter that. There we go. That looks pretty good. So I've got an accurate location and size. So 12 centimeters here, and that intermediate image height is negative 2 centimeters, which I got from magnification 1. It turns out that these two lenses each will magnify separately. We can stack them by multiplying the magnifications together. So that's what I'm going to go for. Now, part 2 of the question is now we have to treat that image like the object for this lens. And so I want to find out what that image distance is. I might call this, this would be, I think, P2, I believe, or the second image distance. That's the way to, or second object distance, I'm sorry about that. So that I'm going to write it out a little bit more explicitly in English there. The object distance for the second lens, the way you get that is, well, it's simply the difference between 40 and this 12 centimeters that we found before. So that's 28. Okay, there's 40 centimeters separation between the lenses. This image is 12 centimeters away, so the remaining distance is 28. And now it's just another lens problem all over again. The second focal length, f2, is 15 centimeters. So let me figure out where the final image distance is going to be. Okay, the same formula as before, but now that's 15, and that object distance is 28, and at the bottom we have 28 minus 15. That should be fine. So at this point, I want to make sure I have a calculator ready and willing to go here. So 15 times 28, delete. 15 times 28 is 420, and 420 divided by 13 is 32. So that means there's some real image, look at this, some real image about here. That's where it'll be. And that's the final location that we're looking for. Okay, so the second magnification, you just use di over do like we always have done with a negative sign in front. The image distance this time, I got 32.3. And the object distance, we use the 28. All right, and I'm going to, off camera, divide those two things. It's going to be pretty close to negative 1.15. It's fairly close to that. I'm going to call this M2, just for completeness' sake. So, yep, that is M2. All right, negative 1.15. So the first lens flipped the image and made it 1/5 the size. This one makes it slightly bigger and flips it again. So you have a right side up image. If you want to know the final, well, here's one way to do it. If you want to get the total magnification, you multiply those two things. So 1.15 times 0.2 is 0.23. All right. My screensaver went on there, and so I just wanted to make sure it's still recording. It looks like it is. Don't want to waste all that good footage. So if you want to know the height of the final image, you can go 10 centimeters times 0.23, and that's 2.3 centimeters. And that's it. Or you can multiply -2 times -1.15 if you want to get the same answer. You can take the height of that middle image and multiply it by just magnification 2, and that gets you to the same answer. So that is the complete problem. I found the image height and location for just the middle one. Then I use this as the object for the second lens and found where the final image is going to be. We can get its magnification and its size. Now, I flip this around. Now there's one version of this problem which I'm not going to draw as carefully to scale, but one that we can think about a little bit. Let's say the same situation, but now let's say you have a diverging lens and then a converging lens in approximately the same spot. I'm gonna draw this a lot more roughly just to make the point. Okay, now with diverging lenses, and I'm going to draw this very, very roughly Diverging lenses have this kind of pattern to them, where you do the sketch, and what you get is a virtual image on the same side of the lens as the object. All right. And so where does that complicate us a little bit? Well, if I want to find where that first image is located, I do FDO over DO minus F. And here's a pesky thing that will happen. That first focal length is -10. So you have to be careful with your minus signs. Like if I were to say that the first object distance is 60 again, let's see what that looks like. So you have -10 times 60 over 60 minus -10, right? Getting those little negative signs is the thing that's the biggest pain in the butt for my students. So you have -600 over 70, and that is approximately equal to, again, I'm using just my calculator off camera, -8.6 centimeters here. And that's fine. I mean, that gives us the positive magnitude that we expect. But what it means is you have 8.6 centimeters there, right? It's like the image is on the wrong side of the lens. And so what that means is the second object distance is actually farther than 40, right? You want to know how far this image is from that lens. So we've got the 40 there, and you have to tack on the additional 8.6. Maybe one way I'd look at it, kind of like the last problem, is 40 minus -8.6, 48.6 centimeters. And that is the object distance you use for the second lens with the positive 15 centimeter focal length. So just watch out for negative signs if you have a virtual image. The image distance is going to be negative, and diverging lenses have negative focal lengths, which will affect you in some places. So I can continue the rest of the problem this way. Just wanted to show you how that setup goes. All right, and that is all. I will now try to edit the sound on this so it sounds proper in both ears. And then I'll post that. We'll see how this goes. If you have any comments on the clarity of either the drawing or the narration, please let me know. All right.